Yes, the 135.
Okay. That way you can hear me just say the whole thing, not just attempting to follow along.
Correct.
And then hopefully, if the recording is actually working this time, at least one of these will be on the recording. Okay, so I am going to replace beta, which is the b, that's the Greek symbol beta. I'm going to replace that with 135 in my equation. So that's 135 equals 10 times the log of I over 10 to the negative 12. So just like in part A, we want to get the log part by itself, so we need to divide both sides by 10. So that gives me 13.5. If it doesn't want me to write the decimal point, why is it not? I can see my mouse. It's not writing. Oh, it wrote up there. Let's try this again. Okay. It doesn't want that decimal again. There's something about that lower part of the screen that it's decided they can't write on. So, okay, so we have 13.5 was log of I over 10 to the negative 12. So to get rid of the log, which is base 10, I want to take an exponent on the 10. So I'm going to raise everything. Each side of my equation are going to be the exponents. So I'm going to write 10 to 13.5 and then 10 to the log of I over 10 to the negative 12. So the 10 is the base, and now my equation is the exponent. So I'm exponentiating, basically. And 10 to a log, base 10, or if you have the log of 10 to something, those cancel. And it won't let me write again. So there's something about that lower part of the screen it decided I can't write on. The 10 to the log, that cancels out. So if 10 to the 13.5 equals I over 10 to the negative 12. So now I'm solving for I, so I need to get rid of the denominator. So I'm going to multiply both sides by 10 to the negative 12. And we're going to use the rules of exponents again, where if you're multiplying things with the same base, you add the exponents. So we would take negative 12 plus 13.5. And that gives us 10 to the 1.5 equals I. So what in the world did the book do? I'm looking at the answer, the textbook. Okay, I see what they did, but that is not how I would have written this at all. Okay, so we get 10 to the 1.5, where if I wanted to put that on my calculator, I can just use the exponent button, and that comes out to 31.6227766, and it's going to repeat equals I. Now the textbook, for whatever reason, decided to write this differently, and they wrote it as 10 times the square root of 10. So that is not how I would write that. It's not an intuitive way, but here's how they basically did it. So we have 10 to the 1.5, and they're basically reversing, splitting this up, so it's 10 to the first times 10 to the 0.5. Because when you multiply the exponents, they add. So they're kind of undoing it. So if you add it on the right, 1 plus 0.5 gives you 1.5. So we're sort of undoing that rule of exponents. So then something to the 0.5 exponent, if I rewrote that, that's as a fraction, that's 10 to the 1/2. Now the 1/2 exponent is the square root. That's the same as taking the square root. So that's where they get 10 times the square root of 10, as they took that 1.5 exponent, split it up, and then turn it into a square root for that 1/2 part. And if you did 10 times the square root of 10 on your calculator, you get the same decimal value that we did before. But I don't think that's an intuitive way to write that answer, and I certainly would accept, ooh, yeah, half of my screen is like disappearing here, and now it thinks I'm trying to take pictures. Okay, I would accept this answer, the 10 to the 1/5 for that, rather than what the book says, which is 10 times the square root of 10. Does that make sense?
It makes sense, but I'm not going to negate that it was a little confusing.
Yeah, I mean, I certainly, had I written this text, that is not what I would have put, and I don't think any professional mathematician would say, you know what, I'm going to make this harder and put it as a square root. There's no reason. We can leave it as a 1.5 exponent. It's completely fine.
Okay, good.
And then zoom in. Okay, so this is 112 from the review, and we've got a wildlife population. A species of bat is in danger of becoming extinct. 5 years ago, the total population of the species was 2,000. The total population of the species are, oops, why? 2 years ago, the total population of the species was 1,400. What was the total population of the species 1 year ago? So we're kind of working backwards here. And so the question is, what kind of model do we have? Because that's the first step when you have a problem and it doesn't tell you. Are you using exponential? Are you using logarithmic? When they don't tell you, that's the first thing you have to do, is kind of figure out what is the model here. So I like to just kind of visualize it with a picture so that I can try to find the right shape. So this is not going to be perfectly to scale, but let's say this is now. And then we have 2 years ago, and then 5 years ago. So 5 years ago, we were at 2,000. Then 2 years ago, we were at 1,400. So if this is 1,000, I'll just estimate it around here. So this would be 1,400. And so you can see that we're decreasing. So presumably we would still be decreasing. This is really bad picture here, but it's going down. So if I had to guess here, I would say, okay, this could be exponential decay because the population is decreasing. We know that we are in the exponential part of the textbook. And so it would make sense. Well, we're in exponential or logarithmic. The logarithmic generally doesn't have a decreasing shape. So like logarithmic graphs generally look like this. So that doesn't quite match what our picture here is. So that is why I'd say, okay, well, this is probably exponential decay, which is decreasing, looking something like this. Now, ours doesn't look exactly like that because we have only 2 points, so we can't really determine what the nice looking shape is. But this at least gives us information here that we can kind of see the general shape. So now that we've kind of determined that, we're going to use an exponential decay model. So exponential decay is where you have y equals, and then I'll say a for the starting amount. And we can do this in 2 ways. We can use a continuous decay where you use the letter E, or you can use any kind of value for R. We don't really know what the rate is. So we can just use R in general. And then to be negative K, well, generally, let's use E because that's usually for population growth. So we will do E to the negative KT. So I'm going to actually go back to where the textbook talks about population growth to kind of show you why I'm using E. I know it's in the textbook somewhere. I just have to find the right part of the book. Those are all compound interest problems. That's radioactive decay. Okay, that is not helpful. It might be in one of the videos. Oh, here it is. Okay. So this is from 5.5, so I'm going to drag it over. So example 2, this is section 5.5, and they don't actually give it to you explicitly, but they're using this model right here. So I'm going to just highlight that. Y equals AE to the BT. So I used K instead of B. The variable there doesn't matter, but that is generally what we use for population, is that we're going to assume that the value under the exponent is E, which is the natural exponent, or the Euler's number 2.71. So they have this example here with the number of flies, and then they're showing that there's this model, but they don't have, like, usually in the book they'll have a thing like, here's this model that you use, but they're only using it based off of this example. But for any population growth or decay kind of situation, this is the model that we generally use. So we're going to use this model. And so I used K, and I made it negative because I know that it's decaying. While here, the number of flies is increasing because it started at 100 and then it was 300. So that's why they have a positive there. But since I know that it's going to be negative because we're decreasing, I can put that negative in there. And then I used just a capital A because that's very similar to our compound interest formula or some of the other formulas that we use. I'm just trying to be a little more, I don't know, consistent. Most textbooks use a capital A in this case versus the lowercase a like our textbook. But the point is not the variables. You can use any letters you want. The point is the form. So I'm going to label this as population decay, so that you know if you see something where you're dealing with a population of items, like the number of things, like you're counting how many things are and you're decaying, you can use this formula. So next is we're going to use our ordered pairs, or we need to find our ordered pairs, and we have to decide how we are going to label our X values, because they've given us now 2 years ago and 5 years ago. So we have a choice. We can make 5 years ago be -5 on the X if we wanted to, and then we could have 2 years ago as -2. We can set now as 0, and then we can set 1 as 1 year ago, which is what the question is actually asking about. It says, what is the total population of species 1 year ago? So if we wanted to, we can set now as 0 and then have negative values as we count backwards. Or if we wanted, we can set 5 years ago as 0 and then count forwards. So it really doesn't matter because you get the same answer either way. It's just a matter of making sure that you are consistent in your labeling. So what makes more sense for you guys? Labeling things and then using years ago as negative, or saying that 5 years ago is 0, and then between 5 to 2 years ago, that's 3 years. So that's going to be 3, 4, and then 5. So what makes more sense to you?
I would do the 0 now.
the way you had originally said it, even though I don't like negatives, but I think it makes more sense because 5 is 5, 2 years is 2 years, and now is 0. I understand.
I agree, because I think most people would label the 2 years as 2 when it's actually 3 years when you're, you know, counting your thing. So I agree with that. So that is what I will do. And it just shows you'll get the same answer regardless. You know, it's actually kind of good to see how you can label these in different ways and still work through the problem. So since we've got that labeled, that allows us, let me pin this so I don't have to keep. Okay, so, and then, oh, I'm like, how do I get rid of this bar on the right? I'll just, there we go. So this will allow us to label our ordered pairs. So we have -5, 2000, and then -2, 1400. So now that allows us to get our ordered pairs, and so we can actually start working with them. So the first thing we need to do is we need to figure out what this K is. And so we do that by plugging in the values, the ordered pairs that they've given us. So we're going to plug in both because we're going to get two, because we actually have two unknowns. We don't know what A is and we don't know what K. We have two unknown values that we're trying to solve for. T, time is our input, Y is our output. So those we want to keep those in our equation, but we have the A and the K we need to figure out. So since we have two unknowns, we need two equations, and so we're going to write them with each of the ordered pairs. So the first one we had was -5, 2000. So I'm going to just plug that into my equation. So 2000 will be the output Y equals, we don't know what A is, E to the -K, and then we know that the time is -5. So I'm going to just simplify that. So we have 2000 equals A, E to the 5K, because the negatives cancel. The other ordered pair we had was -2, 1400. So I'm going to do the same thing. So this is our T, this is our A. So we're going to have 1400 equals A, E to the -K times -2, which gives us 1400 equals A, E to the 2K. So we have two equations here. And so there's a little trick that you can do for solving these. So this is a trick that I generally only use when I'm solving problems like this, is I take the two equations and I divide them. Basically, you can write them as like a ratio. You can divide them by each other. So it's a really weird trick. It's something that you learn just by going through problems like this. Now, if we had labeled our points differently, where the 5 years ago was 0, we wouldn't have to do this trick. But I think this is a good trick to know, because one of the things about algebra is learning the little tricks so that you have more techniques in your little toolbox to try to solve problems. So what I can do is take the first equation, 2000 equals A, E to the 5K, and I could divide that by the second equation, 14,000, and then A, E to the 2K. Now, why am I allowed to do this? So we know that we can divide both sides of an equation by the same thing. So if I wanted to divide both sides of the equation by 2, I can do that. So think of this as I'm dividing one side of the equation by 1400. I can also divide the right side of the equation by 1400, but 1400 is equal to AE to the 2K, so I can just do a little substitution there. So you can take a whole equation and divide it by another equation, essentially. So it's a nice little trick. It's using the same rules of algebra that you've learned so far. It's just not something that you normally see. But what's nice about this is that our variables A cancel out, because we have a on top, a on the bottom. They completely cancel, so we have one variable that we're solving for. And on the left, I can simplify. I can divide 10 out of both of those, so like 2 zeros cancel out. I have 20 over 14. And generally, we're going to use decimals when you have real problems like this. So I can just divide those numbers, and actually it's going to come out. It's not going to come out nicely, so I usually use 4 decimal places. So I'm going to use 1.428, and then that rounds up to 6. So if you do 2,000 divided by 1,400, you get 1.428571429. It will keep going on forever, but I've just rounded it. Oops. Now on the right, the a's canceled. And now we have this trick. It's not really a trick. We're still following the rules of exponents, where if you have the same base and you're dividing, you subtract the exponents. So we'd have 5k minus 2k. So 5 minus 2 is 3. So this leaves us with e to the 3k. So now I have an exponential equation, and I want to get rid of the e because I want to solve for k. And we get rid of the e by taking the natural log of both sides. So I'm going to take the natural log of 1.4286, and then the natural log of e to the 3k. And that natural log cancels out the e, so on the right side we just have 3k. So on the left, I'm going to take the natural log of 1.4286. So I'm going to do that on my calculator. I'm going to get lots of decimal numbers, and I'm going to round it to 4 decimal places. So I get 0.3567, and then I equals to 3k. So now we're just solving for k. So I can divide both sides by 3. And this gives me 0.1189 if I use 4 decimal places. So now I have found k, which is basically the rate at which we are decreasing here. So now that I found k, I'm going to go back up. And so we have these equations here. And so far, if we have y equals a e to the negative kt, we know k. So now we have y equals a e to the negative 0.1189 t. Now we need to find a. So I can use one of these equations. I can either use this equation or this one that I've created. I know k. I can plug in my k, and I have values, and then I can solve for a. It doesn't matter which one we use. So let's say I use the first one. I use the one on the left. 2,000 equals a e to the 5k. So I have 2,000 equals a e to the 5k. So I'm going to plug in my value for k. So I'm going to first multiply the values in our exponent. So 5 times 0.1189, that gives me 0.5945. Now e to the 0.5945, I'm going to evaluate that. There's a button on my calculator that allows me to do that. I want to make sure I type that in correctly. So that gives me 2,000 equals a times, and I get 1.8121 when I round that to 4 decimal places. So now all I need to do is divide both sides so that I can solve for a. So I'm going to divide both sides by 1.8121. And we get 1103.69 equals a. So now I have A, and I could usually, let's round this to a whole number because A is essentially sort of like a starting population. And so that makes sense to round to a whole number because we're not going to have decimal values of whole numbers. So I'm going to just round that one to a whole number because A, that first number is where we're starting with. It's like your starting point. Or in this case, it's going to be the now value. So we have A. So now our equation is y equals 1104e to the negative 0.1189t. Now that we have our equation, we can actually answer the question that was asked. What was the total population of the species 1 year ago? So 1 year ago would be at -1 based off of the way we labeled. So we want to plug -1 in for t. So I'm going to go to my equation. And so I'm going to use my equation. I'm going to plug -1 in for t. And now I'm going to evaluate. So first I need to take care of the exponent. So I'm going to multiply those. Oops, I keep missing numbers. So a negative times a negative is a positive. So I get 0.1189. Now on my calculator, I need to do e to the 0.1189. So that gives me 1.1263 if I round that to 4 decimal places. And then I just need to multiply that by 1104. And this gives me 1243. And I get decimals, but because we're talking about population here, it makes sense to round it. And so I'm going to round that to a whole number. And so we get a final answer for a population for the number of bats 1 year ago as 1,243. So I'm going to just kind of zoom out so you can see all of these steps at once. I know it's going to be really small because I'm zoomed out. Maybe that doesn't work so well. So the process here was first step for the process was to determine what kind of model we're dealing with. And so we determined that this would make sense to be exponential decay. Then we had to figure out how we were going to label our x values or our t values, the inputs. Then we got the equation, the basic equation to use. We had to plug in our information and then do a little trick so that we can solve for k. And then once we knew k, we plugged in the information so we could find A. Once we had both of those numbers, we could get our actual equation, which then we can finally plug in the number that we wanted to answer the question that was asked. The steps or the process here for questions like this where you're doing a model are essentially the same. You're going to have to figure out what it looks like, what the equation would be, like what it should look like. Then you start plugging in numbers, solving for what you need, plug in numbers, solve for what you need, and like that process keeps repeating. So the steps here are the same. It's the hardest part is the fact that you have to figure out, well, what steps do I need to do when I'm doing the solving part? And that's where the algebra comes in. And of course, the little trick that I showed you guys. So do you have questions on any steps along the way here?
No, it's a lot to take in. That's probably one reason why I have a hard time with word problems.
This is also why it's a number 113 and not in the beginning of the review. Yeah, they get easier with practice, basically. The more you do them, the more you see the steps that you have to do. And I know that I say that a lot, but that's really is exactly what's happening. And the more you do word problems like this, the more you get into, oh, I need to do these steps. I need to do these things.